All right, we are back. Well, maybe before we get into the quick math, let me just thank those who have subscribed to the channel and who are liking the videos and sharing it. And I request that the rest of you also subscribe, like the videos, share it with anyone you know doing math, doing technical math. It does help the channel to grow. So I will appreciate that. Okay, let's get back into our video. We are busy with Euclidean geometry. We are doing theorem 3. So for us, this is not one of the ones that we need to prove, but I will do the proof. In fact, I'll show you two proofs in this video. But let's just chat about some of the important concepts. So I'm going to move this angle over here. And what I want us to notice is that it stays 90 regardless of where it goes. Even if I go to the other side, it is still 90 degrees. Okay, so it doesn't matter where I take this third point, provided I have a diameter. What's a diameter? A diameter is a line that goes from one point on your circle, from one point on the circumference, through the center to the other point on the circumference. So provided you have a diameter, wherever your diameter subtends towards will always equal 90. Okay, I used another word there. I'll explain that word as we get into um, our proof, right? So I use the word subtend. What does subtend mean? So let's call this point A and let's call this point B. Where point A and point B go toward. So point A, it goes toward this point. Point B goes towards that point. So point A and point B, they subtend towards this point over here. Okay, so wherever point A and point B subtend towards, because A and B form a diameter. So if A and B subtend towards a random point over here, this point is also going to be 90. Or if A and B together go to this point over here, that point will also be 90. So wherever A and B subtend toward, it's going to form a 90 degrees, right? So that is our theorem 3. So A and B, provided this is a diameter, right? It's a line that goes from one point to the other point through the center. Provided we have a diameter, wherever it subtends towards will form a 90-degree angle. The converse is also true, right? So converse, what is that? That's the reverse. The reverse is also true, that if you have a 90 degrees over here, then you know that this will have to be a diameter. So in case they don't tell me that that's a diameter, if I know that this is 90, let's go back to our picture. If I know this is 90, this has to be a diameter. Or if this is a diameter, this has to be 90. That's basically theorem 3. Okay, let's spend a minute doing our proof quickly. Let's call this A, B, and C. And because we've gone through theorem 2, this can be a very quick one, right? Because this over here obviously is going to be 180 degrees. Okay, let's call O the center. So we are going to say AOB is a straight line, right? Or in fact, let's just say AOB angle AOB is equal to 180 degrees. The reason for that 180 degrees is AOB is a straight line. AOB is a straight line. Okay, that is a straight line. Okay, that's this statement over here. I just put it in our brackets over there. AOB is a straight line. Let's erase it. Okay, so that's the first thing. The second thing, from our theorem 2. Okay, so now we remember theorem 2. Theorem 2 said angle at center is twice the angle at the circumference. So from theorem 2, I know if this is 180, this obviously has to be half of 180. So angle C is going to equal to the 180 divided by 2. How do you know this angle at center? Center is twice angle at circumference, right? Okay, and therefore that is 90 degrees, right? So that's one of our proofs, very quick and easy. that says angle C is half of angle AOB. AOB is 180 degrees. Obviously, it's a straight line. It's our diameter, and therefore C is 90. Right. So when you use this theorem, what you will say, so angle C is 90. And when we use this theorem, we will say angle in a semicircle. Right. So if you're using theorem 3, what you write in brackets as your reason, angle in a semicircle. All right. So that's the one way we can do the proof. There is another way. I'll do that. Let's see if we can do it quickly so that this video doesn't go on for too long. All right. Let's go back to our picture. Let's go. Right, let's get rid of some of these things that we drew in. Okay, so let's name them again. This was O. So I'm gonna do a construction. So I'm gonna draw in something that wasn't there. Let's maybe put this in a different color, and I'm gonna construct line OC. And because of this construction, there are different radii form. There's one, there's one, there's one. Okay, so let's start in this triangle over here. So we will say AOC. In this triangle, we have OA equal to OC. A reason for that is radii. Okay. And because of that, we know that triangle that we have, there's an isosceles triangle. So whatever this angle is going to be, that one is going to be the same thing, right? So let's name it, let's call it X. That's going to be an X. This one is also going to be an X. All right, let's just write that nicely so we can all see that is an X. So we will say angle A equals angle C. We're going to call it X, and our reason that they are equal is angles opposite equal sides. Right. Let's do the same thing in our other triangle. So we see there's another triangle over here. So let's look at this triangle, also an isosceles triangle, right, because of our radii. So let's start by saying OB. Let's use our pen. OB is equal to OC, that is still radii. Right, radii, that's written over there. And then we'll know because of the radii that these angles are equal. Let's go and call them y. So that's going to be y, and this is going to be y. Okay, so let's say angle B is equal to, let's just name these ones because that's there's two C's, so let's not get confused. That's C1, let's go with that, and then this one is going to be C2, and I'm calling them both Y. Reason again, angles opposite equal sides. Okay, so if I go look at my picture, I have an X. Let's see quickly. I have an X over here, I have a Y over here, and this angle over here, angle C, is actually X plus Y. Okay, so I'm just going to draw that triangle for me quickly. So that triangle that we have there is A, B, and C. A, which we called X, B, which we called Y, and C, which we called X plus Y. Right, because C is that whole thing, the X and the Y. Okay, great. Now we look at that triangle, and we know from all triangles that A plus B plus C is going to equal to 180 degrees. So let's say A plus B plus C is equal to 180 degrees. Reason interior angles of a triangle. Right, so let's say A is X, B is Y, C is X plus Y. And all of this is supposed to equal to 180. Okay, X plus X, Y plus Y, that's going to be 2X plus 2Y equals to 180 degrees. Okay, what we're going to do now is to get rid of these 2's. So let's just divide everything by 2. And that will tell us that X plus Y equals to 90. And let's write that again, 90 degrees, right? So what is x plus y? From our picture over there, x plus y is our angle C. So we can say, therefore, angle C is equal to 90 degrees. Right? That is theorem 3. Right? Basically, if you have a diameter, this is our diameter, a line that goes from one point to the other point through the center, wherever it subtends, wherever those two lines go and form, they will form a 90 degrees. The reason that we write down is angle in a semicircle. Semicircle, let me write that again. Angle in a semicircle. All right, great, that's this.